This computer done or going. Um, okay, so a couple of announcements. Number one, you have your first quiz homework type of thing up on Canvas. That will be open for 48 hours. Then the there is another quiz, and this quiz, it's worth 10 points, so you might as well do it and get the points out of it. That quiz is really a matter of, are you set up for Proctorio? Proctorio is the system that we're going to use to take exams. And so that piece of software I'm going to use, and I want you to kind of have a test drive at it. So this is your chance to make sure that the environment you're going to take your test in is the right environment. And that you know how to get in from like a technical standpoint. One word of warning about Proctorio is that if you are prompted for a access code, that means more than likely you need to try using a different web browser, because I'm not going to give you an access code. Instead, Proctorio automatically generates an access code. And if Proctorio can't open, that's when Canvas will say, hey, where's your access code? And that's an indication Proctorio didn't open. Either you have it could be a pop-up blocker or something else that prevents Proctorio from opening. So those two things are open. The quiz that has content from the class is open for 48 hours. The Proctorio one is open until Monday at 11 a.m. They're both open starting at 11 a.m. today. Okay, so with that in mind, I am going to go ahead and begin sharing. And today what we're talking about is measuring matter. So taking something and quantifying it. Now, I've got a survey for you, or I guess a poll quiz. Let's see if this is the right one. Yeah, that's the right one. So kind of reflecting on what we talked about last week. What do you got? If chocolate, we've got a piece of a Hershey's bar there. One cell, it looks like that. Then in the other cell, it looks not like that. Is that an example of physical or chemical change? Chat. Oh, make your response in the poll. Okay, I can give you another like 5 seconds or so. And I'm going to go ahead and 10, 5, 4, 3, 2, 1, 0. Pretty strong contingent of folks voted physical change. And you're absolutely right. Think about this as like an ice cube. Now, that ice cube went from one state to a liquid state. Now, how could it be different? Well, in order for this to be different, or one way that this could be different is if you saw like charred areas around it. That would be an indication, oh, it was burned as opposed to melting. Think about what's taking place. Is it melted? Did it break? Or did it burn or something like that? Okay, so stop sharing. Back. And now we're going to do another one. This Oreo. I had one person message me and they said that they could not see the poll. Does this one show up now? Okay, it showed up. I'm not sure if there's an issue, like if you're using your phone to join the meeting. I think that's all there. It just, you might have to like tap. I can't see the poll either. Um, hmm. If you're using your phone, I always tap my screen and then it brings up maybe other windows that are possible. Okay, give another 5 seconds. 4, 3, 2, 1, and poll. Share the results. Is the quiz due after class or at 11:59? It's supposed to be due on Friday at 11 a.m. It sounds like I need to take another look at the quiz times. Just make a note for myself. So I'll take a look at that after class. Okay, I'll take care of that. Okay, so here we have another physical change. Now, this is kind of tempting, or it's always tempting to look at something and be like, oh, well, maybe there's some sort of molecular bond or something that, broke between these things. And that's an instance where you just kind of overanalyze that sort of question. This is a physical change because try to simplify it for yourself and ask yourself a question like, did it burn? Did it just change shape? Well, this changed shape effectively. It went from one state or one shape to a different state. It just broke or it was broken. Now, with that, let's go ahead and proceed. Now, when it comes to measurement, one of the things that we have to do is we have to have agreed upon units that we use to measure something. Now, if we're talking about the length of something, the unit that we use is a meter. So, the Olympics were this past summer, and so it was the 1,500 meters. That was a road race. The 10,000 meters. That length is a part of the international system of measurement, the metric system. Mass is measured in grams, or what you might also see as kilograms. Again, kind of thinking about the Olympics, you have weight classes of events. 115 kilograms. Okay, thanks for that. I'll take a look at that. Then volume, our conventional or our metric system for measuring volumes is liters. I see in the chat somebody said the quiz times. Thank you very much. I appreciate that. So just take a close look at those, and I'll do the same to make sure that I got them all right. Time is measured in seconds. Now, can anyone think of and add to the chat a unit of time that's, let's say longer than a second? A minute, perfect. What about shorter than a second? Milliseconds, perfect. That's awesome. Oh, wow. Milliseconds, nanoseconds. These are great because that's something that you have a little bit of an idea of using what we're going to be talking about today. Milli, that's a prefix. Nano is a prefix. Now, I think that we all have a tendency to say, oh, a millisecond. I know that that's shorter than 1 second, but how much shorter than 1 second is an important thing to know. How many milliseconds are there in 1 second? Is a millisecond a thousandth of a second? Is it a 100th of a second? Is it 10,000th of a second? That's what we're going to get into a little bit later and use these prefixes. Temperature, well, typically the metric system you're going to use degrees Celsius. And there are some numbers that we're kind of familiar with respect to degrees Celsius. For instance, what is the boiling point of water in degrees Celsius? Add that to the chat. 100 degrees, perfect. So 100 degrees Celsius is the temperature at which water is going to boil. Now, using degrees Celsius, what is the melting point or the freezing point? Those are interchangeable terms. 0 degrees Celsius. Now, that's the metric system. In chemistry, we use something that's a little bit different from that. And the reason that it's different is because we use a system known as the Kelvin system. This is what is known as an absolute system, or an absolute. Yeah. Now, The reason that this is absolute is because, well, the way that I like to think about it is if someone says, I have absolutely $0, I have absolutely no money. What that means is that their buying power is nothing. They can't go to Little Caesars if you want to go to Little Caesars. They can't do anything financially because they have no money. They don't have a credit card where they can borrow money. They don't have anyone that they can borrow money from in any form or fashion. The Kelvin temperature system is very similar to that. This is an absolute system. So let me ask you, what is the lowest possible temperature in a Kelvin system? 0. Perfect. 0 degrees or 0 Kelvin is the lowest possible temperature. Now let me change that and ask you, what is the lowest possible temperature in degrees Celsius? And this is a little bit tricky, but let me rephrase that. A few years ago, when it froze here, or froze in Central Texas, um, it got below the freezing point in Fahrenheit. So it got to like, at first it hit 32 degrees, 32 degrees Fahrenheit, which is the same as 0 degrees Celsius. And then it dropped down to like 19 degrees. And then it dropped down to like 5 degrees Fahrenheit. If 32 is 0 degrees Celsius, then 9 or 5, what would that be in degrees Celsius? Just a rough number. Would it be 0 degrees Celsius? Or would it be lower than that? Like -15. I like it. That's a great. Thank you very much. Exactly. So the degrees Celsius system, you can have a temperature as low as -15. So when I ask you the question, what's the lowest possible temperature in degrees Celsius? Then you're kind of like, oh, as I don't know exactly. The Kelvin system accounts for that. And when you talk about the Kelvin system, you talk about molecules moving and that relating to temperature. And you're saying that absolute 0, the coldest possible temperature measured in degrees Kelvin or measured in Kelvin is 0. Degrees Celsius, well, no one's ever observed something. So it's kind of a theoretical temperature. Negative, and in Antarctica, it gets to -65, -112. It gets to those low temperatures. Is that hospitable to life? No, it's not at all. But it never gets to 0 Kelvin because that's entirely too low for anything to exist. Okay, so those are our two temperature measurements, degrees Celsius or Kelvin, and then the one that we're all familiar with is degrees Fahrenheit. I know I listed 3, but I'm thinking about these in terms of like in a science class, in a chemistry class, what are the temperatures that you're thoughtful of? The last quantity is the amount of a substance. The amount of a substance is in terms of moles. So if you've taken a chemistry class before, you've probably been introduced to a mole. And a mole is a quantity. And this is the thing that I remember in my first chemistry class, I was like, oh, yeah, I kind of get it. But at the same time, I was like, I don't really get it. And that is when someone said, or let me rephrase this. If you have $12, how many dollars do you have? 12. Okay. So a dozen is a word that means something. 1 dozen means you have 12 of something. If you have $2 dozen, how many dollars do you have? And we could do this all day long, where I'm saying 1 dozen equals this, 50 dozen equals this. We could go back and forth because that's kind of a part of our common knowledge. We know what a dozen is. Now, a mole is a number similar to a dozen. One mole of something means a certain number. Now, where it gets hard is when we talk about what that number is. So one mole equals that number. And I'm going to go ahead and scribble this out. Let's say one mole, let's figure out a something, pens. If you had one mole of pens, right here I've got one, you have this many pens. If I remember correctly, this is 602 octillion. So you know how if you have like let's see, I do this with my kids where we talk about numbers. Oh, I would like to have $1 billion. And then the next one of my kids says, well, I want 1 trillion. And then the next says, well, I want more than 1 trillion. I want quadrillion. After a quadrillion is a pentillion, then it's a hexillion, then it's a heptillion, and then it's an octillion. So this is like 602 octillion. It sounds like it's, from a sci-fi movie or something like that. But effectively, it is, I think that 1 octillion is 1 billion billion. It's a crazy large number. So if you had 602 octillion Dr. Pepper cans, that means you have 602 billion Dr. Pepper cans. Now, this is a number that is really tough for me personally to wrap my mind around because it's such a large number. With that, though, we try to make things a little bit simpler and simply say 1 mole of something. Because when we talk about in chemistry, we're talking about particles, we're talking about molecules, we're talking about something that's so small, it's difficult to even visualize or, kind of understand as a concept. So if I say I have 1 mole of something, 1 mole of anything, that means I have 602 octillion. Now, rather than saying octillion, what we do is we avoid writing these zeros by using something known as scientific notation. And if you've taken a chemistry class before, you've seen this number, but it's been converted to 6.02 times 10 to the, does anyone want to add to the chat? If you've taken a chemistry class before, times 10 to the 23rd. Now, that's not, I don't expect you to know that, but I'm just saying, because usually there's somebody who's taken a chemistry class before. So this means this 602 times 10 to the 23rd, the way that I always think about that number is I imagine that whenever I write out all of these zeros, what I'm going to do is I'm going to move this decimal place from here all the way to here. Now, if I move it from here to here, that's 1 time, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. So I moved that decimal 23 places. So this is what's known as scientific notation. Where does the 602 octillion come from? Is there a context or a reference? Kind of like how there's an AU. So that octillion, I was just trying to emphasize what an octillion is. So an octillion is larger than a billion. I'm just trying to stress, like, octillion, we never really talk about that word, but that's simply a quantity. Octillion is not something that I expect you to memorize or anything like that, but I just wanted to give you that for context. Sure thing. Okay, so 1 mole of something is 6.02 times 10 to the 23rd of something. So if I have 1 mole of pens, I have 6.02 times 10 to the 23rd pens. Now, whenever we have a number like this right here, times 10 to the 23rd, that number could be positive or it could be negative. If it's a positive number and you are expanding from scientific notation to long form notation, like what this is long form. If you have a positive number going from scientific to long form, you move the decimal 23 places to the right. So if I were to take this number, like, let's say 1.45 times 10 to the second, add to the chat, anybody, what that number is in long form. 145. Perfect. This is the same as 145. Okay. Now, let's take 1.45 and let's give it a negative exponent. Okay, so if it was positive, I move it to the right. If it's negative, which direction do you think that I should move the decimal? That's right, I move it to the left. So Dylan and Savannah, great job. That's 0.0145. So this is the same as 0.145 or 0. Oopsies. Okay, 0.0145. Great job. Okay, so this is scientific notation. The exponent tells you, are you moving to the right or are you moving to the left? Now, if you're taking a number from long form to scientific notation, that's what you have to account for. How many places did I move the decimal? So it's a little bit tricky. Now, we've got a poll here. So the number 8675309 in scientific notation is 8.675309 times 10 to the 6th. Which number, shown here on the right, is the largest? Now, this is an instance where I would just go ahead and write out the number. Where do I move the decimal? Is there a decimal for me to move? And I'm going to give you about 20 more seconds or 30 seconds. So 25, 24. 20 seconds left. Okay, about 5 more seconds. 4, 2, 1. Okay, I'm going to go ahead and end the poll. I'm going to share the results. Okay, so the answer that most people arrived at, it's okay, don't worry about it, is this one right here, 24,000. Well, let's go ahead and look at B and C. Let's compare these two. Is 240 larger than 24,000? No. Okay, so there we're going to omit 240. It's okay. Don't worry about clicking the wrong answer. For answer option A, okay, we've got 2.4 times 10 to the third. Well, this is one that we're going to go ahead and convert. 2.4 times 10 to the third. Aiden, I believe you're right. 1, 2, 3. So 2,400. Great job, Aiden. That's correct. So I'm going to erase that. Now, Who's ready with answer option D? Aiden, again, is correct. So we're moving it to the left. Whenever I see this negative, I always just visualize it as an arrow. It's pointing to the left. So 1, 2, 3. So 0.0024. So when you see a question like this, I think the first thing that you should do is convert it to long form. And, when you start doing that and you get more comfortable with this sort of question, when you see something like answer option E, let's say 2.4 times 10 to the 37. If you're looking at these answer options and you see, okay, well, 3, I moved it to make 2,400. 2,400 is smaller than C. Okay, so A and B are out, and then D is out because that's less than 1. That's absolutely right, Corey. Times 10 to the 37th. Well, I'd look at this and just be like, I'm going to start 2.4. 1, 2, 3, 4, 5. Okay, 0, 0, 0, 0. I don't even have to write out this whole number in long form. I can know that 2.4 times 10 to the 37th is a number larger than 24,000 and everything like that. So I'm just going to go ahead and breeze through that. Okay, how's that sound for everyone? Give a thumbs up if you're good. Okay, cool. Great. I'm going to stop the share there. And then we're going to move on to our next slide. Okay, so here what we've got is, what's the smallest number? So when we use that negative exponent, we're moving it to the left. So when you're given, stop, Joel. Okay, there we go. When we're given 1.23 times 10 to the negative fifth, what I'm going to do is I can give myself a lot of space. I can say 1.23 times 10 to the negative fifth, 1, 2, 3, 4, and 5. So I'm rewriting this. Here's my new place for my decimal. 0, 0, 0, 0, which is what this says here, but I like to go ahead and, demonstrate that. So we've got 2.4 times 10 to the third, 0.024, 0.0024, and 2.4 times 10 to the negative third. So first step, convert it and see what you got. Well, guys, this is pretty great. I'm going to go ahead and stop right now. The results from our last poll, here, actually, I'm going to go back. I think I can. Oh, no, I can't. In the last poll, it was kind of, it's a little bit split. In this one, it's pretty strong. It's pretty strong in favor of C. Now, let's see if that's the case. For C, we move the decimal. There is 1, 2, and 3. So here's our new decimal place. So 0, 0. So 0.0024 versus 0.00024. So C is correct. Well done, everyone. And for those of y'all who didn't answer C, D came in second. That's pretty darn close. And it's really kind of tough. This is why whenever I get this sort of question, I'll write out the number and I'll take this and I'll say, okay, I'm moving it 3 places. That's 1 place. That's 2. And that's 3. Here's my new decimal spot, 0.0024. So great work, everyone. Okay. Now the next question, so using scientific notation to distinguish a large number from a small number, that's a skill and it takes some work and it takes some practice. I would try using numbers that you see every day and just try converting them. Now, when it comes to writing a number in scientific notation, there is kind of a convention. And what I mean by that is there's kind of like a standard. What that means is that you're going to put one number, the decimal, and then any other numbers. So let's say that we had the number 245. If I wanted to convert that to scientific notation, this is where my decimal place is. I'm moving it 1, 2. So I'm going to say 2.45 times 10 to the second, because I moved my decimal place 2 spots in order to make it look like, or for this, I moved it 2 spots to make it look like that. Now, if I had, let's say, or sorry, I just want to clarify that you have one number, the 2, a decimal spot, and then trailing numbers. Here's our trailing numbers. This is different from, I want to make sure that nobody makes this mistake and says, oh, 24.5 times 10 to the first. You wouldn't do that. You always put one number to the left of the decimal and then everything else. So this is correct. And then this one is frowny face. Not correct. So smiley face, correct. All right. Now, the next thing that we're going to talk about that's a little bit related to quantities is our prefixes. Now, whenever I asked about numbers and asked about times, there are people who said a millisecond and a nanosecond. These numbers mean something because a millisecond is the same as 1/1000th of a second. A nanosecond, for example, is even smaller than that. Now, the way that I always think about these prefixes, kilo, milli, nano, is I try to think about the base unit. And I'm going to jump ahead. We're not going to do this poll. I'm going to jump ahead and show you this. This is the range that, or this is kind of all of the prefixes that you can possibly come across, or that are most common to come across. What I want you to be able to convert from and within is kilo to micro. So the way that I always think about this is I think about quantities that I see somewhat regularly. For instance, this is a 16-ounce Dr. Pepper can. If you look at the side of it, it might not be, 473 milliliters. Okay, so 473 milliliters. My prefix is milli, ml. This is the same as 0.473 liters, because in 1 liter, there are 1,000 milliliters. In 1 milliliter, there are 1,000 microliters. Here is the symbol for micro. Here's the symbol for milli. Then what I will also think about is units like centi. Well, we've heard a centimeter. Well, cm. You've probably seen a meter stick. There are 100 centimeters in 1 meter. There are 10 decimeters in 1 meter. If you have in 1 decameter, meter, that is equal to 10 meters. Has anyone ever watched the TV show Breaking Bad? Usually people have seen that. I've not. But when it comes to Breaking Bad, well, they're talking about drugs. And what's the quantity that they talk about quite often? Or any movie where people are selling or moving drugs. They talk about kilos. So 1,000 grams is equal to 1 kilogram. So your base unit here is 1 gram. just as your base unit would be 1 meter. You go up and you say, okay, well, 100 Hg is greater than 1 gram. That's 100 grams. 1,000 grams is equal to 1 kilogram. 100 grams is equal to 1 Hg, 1 hectogram. So these quantities, being able to navigate between them is an important thing that I want you to be able to do. So when you see these sorts of numbers, think about, well, milli. That's smaller than 1 base unit. If you go and you get a Tylenol or something or an aspirin, you're probably going to take about 250 milligrams, which is the same as 0.25 grams or 0.250 grams. So one of the tricky parts about this plot here is the symbols associated. So lowercase g versus capital G. That's the difference between a gram and a giga. Giga is a prefix, a gram is a measurement. Lowercase k, well, that refers to kilo, a prefix. Capital K refers to temperature, a Kelvin. Lowercase m can be either meter or millimeter, which is why when you see something that is 1 millimeter, it's 1 mm. Capital M can be mega. Now, if we look at something like this, what is the mass of this apple in scientific notation? Shows up on this digital balance as 172.3 grams. Well, we can rephrase that using scientific notation and write it as moving the decimal 1, 2 places. So 1.2 or 1.723 times 10 to the second grams. And in this case, we're going from scientific notation to complete notation or full notation. So that's why we use a positive value there, or that's why we're moving it to the right 2 places. What about in kilograms? So here what we can do is 1.723 grams, or 1.723 times 10 to the second grams. That is equal to 172.3 grams, which is equal to 0.1723 kilograms. So we've done scientific notation and prefix notation in these conversions. Now, this is going to be a part of the next quiz that you're going to see on Canvas, where you just have a couple of examples of converting scientific notation and using these prefixes. Now, again, the range that I want you to be familiar with and be able to move between is micro to kilo or to kilo. What I'm probably going to ask about are milli to the base unit, so milligrams to grams, and then grams to kilograms. Being able to do that is an important thing. Okay, now measuring volume. What is the volume of this liquid in milliliters? So this is a 50 milliliter graduated cylinder. This is 45.0 milliliters in terms of liters. So 1,000 milliliters is 1 liter. So if this is 45 milliliters, well, then what you have to do is you have to move this decimal place. So this would be 0.045 liters. What I always do is I think about, well, 100 milligrams is equal to 0.1 grams. So then when I see a number like this, I've got my milli prefix, 45 milli is equal to 0.045 liters. That's one that I try to do kind of regularly in my head, making this conversion from milli to liters. 1,000 milliliters is equal to 1 liter. Here, what we have is measurements using centimeters. So 0 centimeters up to 17.35 centimeters. So here is 17 centimeters, then put 1, 2, 3, and the end of this is between the 0.3 and 0.4. So inches, this is going to be 6.831 inches. Measuring time, we're doing a conversion from 6 minutes and 31 seconds. Well, 6 minutes, 1 minute has 60 seconds. That would be 360 seconds plus 31 seconds is going to be 391 seconds. The next one is measuring temperature. And actually, let's use this scale real quick. So we talked about our temperature measurements. We have Celsius, Kelvin, and Fahrenheit. Those are the big three. Fahrenheit, we have a boiling point of 212 degrees Fahrenheit. We have a freezing point of water of 32. And we have to memorize these measurements, or we have to use a measurement chart for quizzes and exams. In terms of conversions, this, you know what? Giving it some thought. I'll give you this on an exam. I'll give you that on an exam. And that's not, I'm not saying that like I'm going to make it really hard or anything like that, but you can have that. So this is almost like I'll give you the information on your exam, but you have to be able to use it. I got a question, a private direct message that was, will you have to memorize these measurements, or will you be able to use measurement chart for quizzes and exams? So what you need to focus on is converting between these. So if I say something weighs 1.3 kilograms, how many grams is that? How many milligrams is that? How many centigrams is that? Does that sound good? Add to the chat a thumbs up if that sounds good. Or on video, just give a thumbs up. Thumbs up. Okay, cool. Okay, good deal. And I'll capture this and put this on the quiz that I'm going to be posting for Friday, so that you'll be able to work through that. So see some examples of that. And I think that, yeah, so next up is this right here, converting between temperatures. So if something is Kelvin, Celsius, or Fahrenheit. Kelvin and Fahrenheit, or Kelvin and Celsius are right next to each other. The reason for that is because converting between them has kind of a set standard. If water boils at 100 degrees Celsius, then, or sorry, the conversion to that in Kelvin is 373. Okay. If water freezes at 0 degrees Celsius and it freezes at 273 Kelvin, what do you think the conversion from 55 degrees Celsius to measurement in Kelvin is? What is 55 degrees Celsius in Kelvin? Add it to the chat. Base it on 328. Okay, I like it. Perfect. Caitlin added the equation. That is 55 plus 273. You're absolutely right. Because you can use 100. What do you have to add to 100 to get 373? 273. What do you have to add to 0 to get 273? 273. So anytime that you're trying to make or determine a temperature in degrees Kelvin, all that you're going to do is take the temperature in degrees Celsius and add 273 to it. Now, that's a number, that 273, that you're going to have to commit that to memory. So what this shows us is that degrees Celsius, or the lowest theoretical temperature in degrees Celsius is negative 273. Because if you add 273 to that, we get to our lowest possible measurement in Kelvin, which is 0 Kelvin. Because the Kelvin scale is an absolute scale, which means that we cannot have, there's no such temperature as negative 15 Kelvin, negative 28 Kelvin. You're not going to have a temperature that's negative in Kelvin. Okay, now if we jog back, measuring temperature in Kelvin, that's all that there is to it. Making conversion from degrees Celsius to Fahrenheit gets really kind of wonky, because if you look at the difference between 0 degrees Celsius and 100 degrees Celsius, so these major points of boiling point of water versus the freezing point of water, the difference is 100. Now, most of the time when we work with numbers, we're talking about what's called a base 10 number system. Well, with Fahrenheit, we don't have that. Instead, it's a 180 degree difference. Now, I'm not going to be asking you to convert between degrees Fahrenheit and Celsius. I will ask you about converting from degrees Celsius to Kelvin, though. So make sure that you can do that. But I would definitely know this temperature, and then all of these temperatures that are on here. Now, all of these that I've highlighted over here, if you're provided with the temperature in degrees Celsius, you can very easily come up with a temperature Kelvin, because it's just add 273. If you're given the temperature Kelvin and you're asked for the temperature in degrees Celsius, it's minus 273. So it's pretty simple and straightforward there. Now, that is where we're going to stop today. But before you leave, I just want to say that on Friday, you're going to have a pre-recorded lecture. So we will not be having our 10 a.m. Zoom meeting. So I will be posting that pre-recorded lecture before Friday morning. So you'll have access to it so you can watch it, either get started early or whenever. You have a quiz that goes live at 11 a.m. I got to confirm those times. And then it closes on Friday at 11 a.m. I will be posting another quiz, and I'll give you an announcement alongside that quiz. And that will be going over scientific notation and prefixes. So make sure that you get some practice with those. Then last but not least is, no, I think that's, oh, last but not least is make sure that you do that Proctorio practice quiz. Think about it as, I'm doing this in the exact same setting that I'm going to take my exams on Proctorio. So I would highly advise using a quiet area as opposed to like, well, I'm going to go sit at the Starbucks, because then there's going to be lots of activity. Then it's going to flag and say that, oh, it's going to give me alert, and it's going to say this person is possibly cheating. Okay, so the quizzes are going to be 2 attempts. Am I going to change the date for the quiz today? I'm going to go back and look at it and make sure that it goes live today at 11, and then it closes on Friday at 11. So someone told me that it was good, but I'm going to look at it, make sure that it's all right. So if there are no other questions, I hope you have a wonderful afternoon. I'm going to stop my recording right